17th lecture today on the 2nd of February, and we continue our discussion on double tuned circuits. I first briefly recall what we did the last time. We had a double tuned circuit like this. We had a VI, a resistance, a capacitance C, and an inductance L. The secondary was an identical tuned circuit L, C, and the output was taken across R. This was V0, identical tuned circuit with dots like this, M equals to KL between these two, and we had assumed two currents I1 and I2, wrote the loop equations and found out the transfer function V0 by Vi H of S as equal to A S cubed divided by S minus S1, S minus S1 star, S minus S2, S minus S2 star, where capital A was expressed in terms of the damping coefficient and the natural frequency as twice zeta omega n k divided by 1 minus k squared, and S1 S1 star was equal to minus zeta omega n divided by 1 minus or 1 plus k plus minus j omega n. It really does not matter S1 S1 star because S2 S2 star also comes, j omega n square root of 1 by 1 plus k minus zeta square divided by 1 minus 1 plus k all squared. It should be plus throughout, and if we had S2 star, okay, the only change is this sign changes to minus, this sign changes to minus, and this sign changes to minus. Okay. So these were the poles, and then at this point of discussion we made a certain approximation. We said that zeta squared is much less than 1. That means it is an under damped case. Okay, zeta squared is much less than 1. We also assumed that the coefficient of coupling k is also much less than 1. That is, the two coils are loosely coupled to each other. All right. Under this assumption, the poles. How can we say this? Zeta equal to 0 of course is underdamped, right? Zeta equal to 0 is undamped. Zeta equal to 0 means there is no resistance, so there is no damping. Zeta much less than 1 means zeta tends to 0, and therefore it must be underdamped. Okay. With this assumption, we approximated S1 S1 star as minus zeta omega n plus minus j omega n, then 1 minus k by 2. You should understand how this minus sign comes. It is 1 plus k to the power minus half, and that is why 1 minus k by 2 comes, and S2 S2 star is approximately equal to minus zeta omega n plus minus j omega n 1 plus k by 2. And we notice that the pole locations are such that they all lie on a line parallel to the j omega axis at a distance of zeta omega n from the origin, and that they are symmetrically located with respect to j omega n, one on this side, one on this side, similarly one on this side, one on this side, such that the difference, the distance between them is given by omega n times k. One is below omega n k by 2, and the other is above omega n k by 2, and therefore this distance is omega n times k. This is the location of the poles, and this was shown. In addition, we have 3 zeros here. This was shown in an enlarged form in this slide. Okay, this slide shows the the two poles in a slightly enlarged form. Zeta omega n has also been enlarged. Actually, it's very close to the j omega axis. Enlarged form to show you the 4 vectors which determine the magnitude. 5 vectors. One is m0, because there are 3 zeros, m0 has to be cubed in the numerator. Then in the denominator we shall have m1, m2, m3, m4. And we also made the assumption that if zeta is much less than 1, zeta squared much less than 1 and k much less than 1, then and omega is close to omega n, omega is close to omega n, if omega is close to omega n, then it is these 2 vectors which determine the magnitude response and also the phase response. The other vectors can be approximated, m0 can be approximated by omega n, m0, m3 and m4 being very close to each other and being very close to the j omega axis, the poles being very close to the j omega axis, can be approximated by twice omega n, and therefore the approximations that we used was m0 approximately equal to omega n, m3 and m4 both are approximately equal to twice omega n, and under this condition the magnitude function, the magnitude of the transfer function was approximated as a omega n divided by 4 m1 m2. Did we come up to this last time? Yes, we did. Okay, which shows that what we have done is approximating the double tune response by that of a single tune circuit. In single tune also the amplitude, the magnitude was k by m1 m2. Here also it is m1 m2. m1 is a function of omega, m2 is a function of omega. The only difference is that instead of this center point at origin, here the center point is at omega n, and therefore all the concepts of picking circle should be valid here also. Okay, let me show a typical situation. Yeah, I'll come to this. Here we have assumed this is a typical situation. Omega n is the center frequency, omega n, and then I have the 2 poles, red crossed ones, these 2 poles at a distance of omega n k from each other. This is minus zeta omega n, and here we have assumed that zeta omega n is greater than omega n k by 2. In drawing this diagram, we have assumed that, I am sorry, it is the other way around, omega n k by 2, this is the center and this is the radius. Radius is omega n k by 2. We assume that omega n k by 2 is greater than zeta omega n, so that there are 2 intersections with the j omega axis. There are 2 intersections, and these intersections are called omega 2 max and omega 1 max. All right. At both of these points, the magnitude will be a maximum, because this angle psi, the derivation of which we are coming to in a moment, this angle psi is 90 degrees here. This is the diameter and this is an angle subtended on the circumference, so the angle psi must be pi by 2. You also realize before passing further that this circle may or may not intersect the j omega axis. Depending on the relative values of k and zeta, this circle may or may not intersect. This situation is when omega n k by 2, that is k, is greater than how much? Twice zeta. This is a situation when the coefficient of coupling is greater than twice zeta. Omega n k by 2 is greater than zeta omega n, so k is greater than 2 zeta. If k is equal to 2 zeta, then this circle shall touch the j omega axis at omega equal to omega n, and when k is less than 2 zeta, then the circle will not touch at all. It will cross the real axis at a certain point, but it will not touch the j omega axis. So one is tempted to conclude that if this circle does not intersect or touch the j omega axis, there should be no maximum. There should be no peaking. But the situation is slightly different here. I think we left at this point.
So can you explain this again? I mean, what case there will be maximum?
I am coming to in details. I just wanted to mention this briefly here. You see, depending on this radius, this circle may or may not intersect the j omega axis. And the three cases that arise we will come to a little later, but let us do a little derivation assuming that they do intersect. Okay? In other words, our poles are, let us say, somewhere here. This is my sigma axis, this is omega n k, and this is the peaking circle. This is the peaking circle. This is a general point at which we draw the vectors and we call them m1 and m2. The angle included is psi. The angle included here is psi, and this point is what? Minus zeta omega n. All right, and we have already seen that the magnitude h of j omega is equal to capital A, not capital A, yes, A omega n divided by 4 m1 m2. Now, in a similar manner as we did in the single tuned circuit,
The horizontal axis will be j omega n, the center point.
yeah, this is j omega n, quite so. We will call this intersection as j omega 2m 2 max and this intersection as j omega 1 max. All right. The origin here, the crossing that is shown here is j omega n, quite correct.
You labeled it sigma.
This sigma is okay. I can draw the sigma axis anywhere I like. Okay. Sigma is okay in the horizontal line. This point is j omega n. Sigma equal to 0 here. This is perfectly all right. But this point is 0 j omega n. Okay. Now, the area of this triangle, let me show this. We can calculate the area of this triangle in two manners, exactly like in the single tuned circuit. The area is obviously half, triangle is equal to half, the base is omega n k, base is omega n k, and the height is zeta omega n. Therefore, this is equal to omega n squared k zeta divided by 2. All right, and it is also equal to a triangle with the two sides given and the included angle. So, it is half m1 m2 sine of psi. This is simple trigonometry, and therefore I get the value of m1 m2 from here. M1 m2 becomes equal to how much? Omega n squared k zeta divided by sine psi. All right. Let me substitute this m1 m2 in this equation, that is the equation for h of j omega. If I do that, then I get the following result. I get magnitude h of j omega as equal to a omega n divided by 4, then 1 by m1 m2. So, I shall have sine psi divided by omega n squared k zeta. If one recalls that capital A is nothing but twice zeta omega n k divided by 1 minus k squared, substitutes this here and makes all the cancellations that are due, then this simplifies to a very simple expression. It simply becomes sin psi divided by 2 1 minus k squared. It becomes independent of zeta now. We have of course assumed that zeta squared is much less than 1. It is only dependent on k, and therefore if you agree, we shall conclude that the magnitude, you must not forget the assumptions. It is not the general magnitude. It is not the magnitude at a general point on the j omega axis. It is a point close to omega n. Okay, it is a point close to omega n under the assumptions that zeta squared is much less than 1 and k is much less than 1. The magnitude is basically determined by a single variable, namely psi. And of course, the maximum h of j omega max occurs when psi is pi by 2. So, this is 2 1 minus k squared, and the half power points shall occur when psi is pi by 4. Psi is pi by 4, and you can draw the half power points in exactly the same manner, half power circle in exactly the same manner as we did earlier. Namely, what we do is we take this as the radius, the intersection on the sigma axis as the radius, and as the center, this as the center and this as the radius, distance from here to here, and then draw the circle. These two will be the half power points if the picking circle intersects the j omega axis at 2 points. If the picking circle intersects the j omega axis at 2 points, then these two shall be the half power points. The case is slightly different from single tuned circuits because of the fact that 0 has been transferred to omega n, 0 has been lifted to omega n, and because of another fact. Let me highlight that fact. In the single tuned circuit, you recall, if the output voltage was taken across the capacitor in the single tuned circuit, then the transfer function was of the form some constant divided by s squared plus twice zeta omega n s plus omega n squared. K was equal to omega n squared, and therefore the DC response was equal to unity. On the other hand, here we are taking the output across the resistance, and the transfer function is of the form as cubed divided by a fourth order polynomial, and therefore the DC response is 0. Therefore, the conclusion is the DC response is 0, infinite frequency response is 0. So, whatever be the values of k and zeta starts from 0, magnitude cannot be negative, it goes to 0 at infinity. So, in between there must be a maximum. Is that clear? No? Okay. The difference between single tuned circuit and the double tuned circuit is that the transfer function in the double tuned circuit has an s cubed in the numerator, okay, and in the denominator it has an s to the fourth. Whereas in the single tuned circuit, the case that we considered, we took the voltage across the capacitor, V0 was here, and the transfer function had a constant in the numerator. So, the DC response, that is, put s equal to 0, s equal to 0, this value is 0. The double tuned circuit DC response is 0. So, it starts from 0. At infinite frequency, when s goes to infinity, the highest power term in the denominator dominates. So, we get s cubed over s to the fourth. So, as s goes to infinity, the magnitude must go to 0. Alright. So, it starts from 0, it goes to 0. Alright. Therefore, in between it must show a maximum, there is no other way. at least one maximum, at least one maximum. There can be other maxima also, as you will see in the picking circle. Whereas in the single tuned circuit, the response starts from unity. Now it goes to 0 at infinity. In between, it may either show a maximum or may not show a maximum. Alright? Whereas in the double tuned circuit, there must be a maximum. It cannot be otherwise. And therefore, in the double tuned circuit, irrespective of the values of k and psi, k and zeta, irrespective of the value of k and zeta and the relations between them, whether k is greater than, equal to or less than 2 zeta, whether the picking circle intersects the j omega axis at 2 points or not, whether it touches at one point or it does not touch or intersect at all, it does not matter, there shall always be a maximum. If there is a maximum, there must also occur 2 half power points. 2 in the case of a single tuned circuit with output taken, I am repeating this, output taken across a capacitor. If the output was taken across the resistor, situation would have been quite similar to here. If the output is taken across a resistor, you would have got a band pass response, truly band pass response, and there would have been a maximum. Okay. If the output is taken across a capacitor, there may be a peak, there may not be a peak. If there is no peak, then obviously only one half power point. Even if there is a peak and the peak is less than root 2, then also there shall be only one half power point. Alright. Whereas in a double tuned circuit, irrespective of what you do, there shall always be at least one maximum, at least one. At least one maximum, 2 half power points. At least 2 half power points? Yes, there can be 4. We will come to this. There can be 4 also. Alright, we will come to this. Now, let us go back after this qualitative explanation of why there should be a maximum and why there should be at least 2 half power points and the difference between STC and DTC. Let us look at the actual situation depending on the values of k and zeta. You see, in the first figure, the picking circle does not touch or intersect the j omega axis, which means that for this k is less than 2 zeta. Is that clear? K omega n by 2 is less than zeta omega n, so k is less than 2 zeta, which is called the over. Okay, no more damping. We are assuming that damping is small because we have got complex conjugate pairs of poles. This discussion is all based on the assumption that there are complex conjugate poles. So we take damping away from our consideration. We now only depend on k. Why? You saw the magnitude has been expressed now as sine psi divided by 2 times 1 minus k square. So zeta has been dropped out of the picture. Zeta is low, that is assumed low enough to produce complex conjugate pairs of poles and approximation of the poles by the expressions that we have already indicated. Zeta is low enough. Okay. Zeta is now out of the picture. Now we have to talk about k. Zeta is fixed quantity now for all these. Zeta does not vary. What varies is k. Now if k is such, if k is less than 2 zeta, then this is called, there is no peaking, there is no, the peaking, no, I am sorry, I should modify this statement. The peaking circle does not touch or intersect the j omega axis. Obviously k is less than 2 zeta in this case, and this is called the undercoupled case. Undercoupled. This is undercoupling. Undercoupling means that k is less than 2 zeta. Physically there are two coils which are brought close to each other to interact with each other. Alright. Suppose they are taken far apart so that k is 0. Obviously each tuned circuit will behave will show its own behavior. Alright, and therefore there shall be only one maximum and two half power points. Agreed? So this is called undercoupling, and the extremum value of undercoupling is obviously k equal to 0, no coupling. Both tuned circuits behave in their original manner, they don't interact with each other. Now the situation changes when the peaking circle just touches the j omega axis, and this touching must be at omega n. One more point. One more point. You can easily show by geometric construction that the angle psi between the two vectors m1 and m2, this angle is highest at omega equal to omega n. As you go this way, the angle goes on decreasing, and therefore the maximum, as is justified by common sense, when k equal to 0, obviously the maximum shall occur at the natural resonance frequency of the tuned circuit, that is at omega n. Alright, so the maximum still occurs at omega n. As long as k is less than 2 zeta, the maximum occurs at omega n. Alright. Now if you go here, the maximum obviously, now here psi max cannot reach pi by 2, and therefore the maximum is less than what would have occurred otherwise. Okay, we will show this by a picture later. So there would be a maximum, but this maximum value would not reach the highest possible value. Highest possible value is reached here when k is exactly equal to 2 zeta, so that the peaking circle touches the j omega axis at just one point omega n, and this angle obviously is pi by 2, because it is an angle subtended by a diameter on the circumference. Alright, this angle is pi by 2, and therefore there shall be one maximum, there shall still be two half power points. Here also there is a maximum, there shall be two half power points, and these half power points, if you exert a little, can again be found by geometrical means, but I will not discuss that. I will leave that to you as a problem, exactly like the single tuned circuits. Yes?
So then we drawn by taking that omega n as the center and taking the...
We will leave that to you. Okay. Unfortunately, only 2 people responded to my earlier challenge. I want more responses. Otherwise, it becomes a dull class for me. Unless you come out with my expected answers or counter to my answers. I may be wrong, and if you can prove that I am wrong, that gives me the greatest pleasure, rather than verifying what I said is true. No, that I know it is true, so what is so big about it? Okay, come back here. I leave that to you as problems. Okay, finding out the by geometrical construction, perhaps without going into the mathematical derivation. The other 2 answers that I got, they were suggested by the mathematical derivation. Perhaps one could do it otherwise also. Alright? Because all it amounted to was finding another point psi where the angle is pi by 4. Okay? So by geometrical construction you should be able to do that. Now, coming here, the maximum occurs at omega n. Here also maximum occurs at omega n, but this maximum is greater because sin psi reaches its highest value, that is unity. Here it cannot, because this angle cannot be pi by 2. On the other hand, if the peaking circle does intersect the j omega axis at 2 points, omega 2 max and omega 1 max, at each point the angle is pi by 2, and therefore there would be 2 maxima. And if there are 2 maxima, in between there must be a minimum. Agreed? In between there must be a minimum, and therefore here is a situation when instead of 2 you may or may not have 4 half power points. Now the minimum by symmetry obviously shall occur at omega n. Okay, if you go on drawing the angles, it's very easy to show that this angle psi shall reach the minimum value at omega equal to omega n. If this minimum is less than, mark my words, if this minimum is less than 1 by root 2 times the maximum value, then obviously then there shall be how many? 4 half power points. If it doesn't, then 2. Okay, there shall be a dip in between. Now let us see what let's see by means of a diagram. Okay, the green here is the undercoupled case. Undercoupled means K. What is undercoupled? K less than 2 zeta. It reaches a maximum, but this maximum is not quite H max, which can be achieved. On the other hand, when K equal to 2 zeta, that is the critically coupled case, there is the maximum value occurs again at omega n, but it reaches the highest possible value. Highest possible value is 1 by 2 multiplied by 1 minus K square. Okay. When it is overcoupled, when the coils are brought close to each other, that is K is greater than 2 zeta, this is the overcoupled case, this single resonance curve now flattens in the middle to make way for 2 maxima. And obviously, as you can see here, there shall be only 2 half power points. Okay, this is less than, this is not 70.7%. There shall be only 2 half power points. And irrespective of the value of K, irrespective of whether it's an undercoupled case or critically coupled case or overcoupled case, we shall have 2 half power, at least 2 half power points. Alright? And if we have 2 half power points, naturally we can determine for overcoupled case there can be 4 half power points.
The omega max are symmetrical.
Omega max are symmetrical. This happens. Yes, omega. Can anybody answer this?
Because of the assumption.
K by 2.
That is right. Because the poles have been made symmetrical by that approximation.
Omega and K by 2.
That's right. So everything would be symmetrical. This would be, this curve shall have arithmetic symmetry. You see, the distance between omega n and omega 1 max, omega 2 max will be the same. Let's find that out. Let's take, that's a good question. Is there any question about this curve? It can be physically observed. It takes very little hardware to actually carry out the experiment. There are coils in the laboratory. You go to the electronics lab, ask for 2 coils, bring them close together, put the identical capacitors in the circuit. Don't use any external resistance, because the coil resistance is enough to take care of the capital R, and then you can actually observe this double picking.
Sir,
Yes.
so all these will go 0 at 0 only, because they are intersecting the 0 axis at different points.
Well, this starts from the origin. I don't have all the 3 colors, but let's see. The green one, for example, it goes like
That means
this.
it is too small.
Too small, so it has not been plotted. Okay, they will all go to 0 at origin and also at infinity. All right. Any other question?
So is it possible to have 3 half power points at a point exactly where it is 1 by root 2?
Very good. Yes, it is possible. If the dip is exactly 1 by root 2 times the maximum, 3 half power points. Yes. That is correct. But in every case, well, usually one does not want. All right. Let me now talk about a bit of practical sense. You see, with a double tuned response, with a double humped response, this is called double hump. Okay, omega, and let's say we have the response like this. Suppose the hump is like this. This is the maximum, and 1 by root 2 is somewhere here. This is max, and this is max by root 2. Well, such a response is hardly of any utility. Such a response is hardly of any utility, because you can't say this is the bandwidth. Within this band, there is a band which falls below 3 dB. Isn't that right? And therefore, the group of frequencies situated between these are not passed almost equally. However, the response that is of greatest interest is when this is almost flat. cannot be achieved in practice, but you can achieve something like this, a small dip, alright, and the curves will follow like this. Once again look at this. This is the case when critically coupled, okay, when it's critically coupled. When k, this is k equal to 2 zeta, when k becomes slightly greater than 2 zeta, well, maybe the curve goes like this. When k goes higher than this value, the blue curve, perhaps it goes like this. Maxima are the same, but the dip is higher. Okay, and then it goes on, this phenomenon goes on as we make more and more tightly coupled, as we bring the coils closer and closer together. The dip in between and the separation between the dips, between the peaks, increases, separation increases.
So can for same dip we can increase the separation between two peaks?
No, not with the same coils, you will have to change the coils. Okay. Now what I said was the case would be of maximum interest when between these two frequencies, between the two half power frequencies, omega C1 and omega C2, the amplitude response, the magnitude response lies within 3 dB. If this dip goes below 3 dB, then we lose interest. Okay, and this is used for so called wide banding techniques, wide banding. For example, take the broadcast band, one of the medium wave broadcasting centers, Delhi B, for example. Delhi B is 1000 kilohertz, 1000 kilohertz, let's say. Now 1000 kilohertz, one might think that a single resonant circuit having a high Q at 1000 kilohertz should be good enough to pick up this station. But 1000 kilohertz is not 1000 kilohertz. It is modulated by music, speech, whatever you want to transmit. And therefore, there is a certain non-zero bandwidth. Okay, maybe 1000, the actual spectrum, if you take the Fourier transform of what you receive, the actual spectrum would be 1000 plus minus, let's say, FM, where FM is the maximum modulating frequency. And therefore, to tune to 1000 plus minus FM, you do require not a very sharp fall, all right, to discriminate against the adjacent, let's say, Jaipur center or some other center, but in between you require that this band should cover not just 1000 but 1000 plus minus FM. And this is a typical use. There are many other uses where where one wants a band pass response like this. Ideally, what you require is something like this. That is, you want to pass a certain band of frequencies and reject others. All right, and the double tuned circuit gives you a reasonably good approximation like this, where this level should be between 3 dB, 0 dB and 3 dB. Okay, so that is the use of a double tuned circuit. And the IF coil in the radio receiver, it's an example of two coupled coils. The IF stage of the ordinary receiver, okay, either in TV or in radio, is an example of a double tuned circuit. Double tuned circuit is an extremely interesting circuit to experiment with and have fun in the laboratory. Even if it is not set as one of the experiments in the lab, you can ask the lab technician, and I am sure the teacher will be very pleased if you say, I want to set up this and observe this. Okay. Now let us look at the look at the values of the two maxima. If there are two peaks, the values are like this. You have the poles and the picking circle is something like this. This is zeta minus zeta omega n, and this is omega 2m, j omega 2n. I am not writing omega j, and this is omega 1n. We are interested in finding, this is omega n. We are interested in finding the value of omega 2m. Okay, obviously it can be found out from this right angle triangle. You can write omega 2m minus omega n whole squared, that is this squared, equal to zeta squared omega n squared, zeta squared omega n squared, this distance squared, minus of this, plus what is this? This is the radius, omega n k by 2, so omega n squared k squared divided by 4. By simplifying this, you can find out omega 2m as equal to omega n minus or plus? Common sense, it is above omega n, so it must be plus. Plus omega n square root of k square by 4 minus zeta square. Okay, and obviously omega 1m, this maximum shall be symmetrically located with respect to omega n, so it should be omega n minus the same quantity. These are the expressions for the two peaks. One must not lose sight, however, of the assumptions. Assumptions were that the damping was very small and the coupling was loose, but at the same time double picking occurs for over coupled case, over coupled under loose coupling. Okay, loose coupling has 3 stages: under coupled, critically coupled, and over coupled. Now over coupling may be increased to an extent that all these assumptions go down the drain. Then none of these expressions will be correct. Is that clear? If you bring them too close to each other, then there will be sharp picking, but in between the dip will come so low that the circuit would be useless, and therefore these are to be decided from experimental considerations, that is by trial and error, by bringing them close together and so on. There is no clear analytical expression between air space between the two coils and the coefficient of coupling. You can derive it, but it's not useful. It's not useful. Yes, there is a question.
So loose coupling depends only on the value of K. So while
K depends on
yes sir, K depends on loose coupling.
loose coupling. Yes.
So what overcoupling can be increased by decreasing psi.
Overcoupling can be increased by
decreasing the damping coefficient.
okay. Since he has a point. You see, since it's a relative value of K and 2 zeta, now I want K greater than 2 zeta. I can do this either by increasing K or by decreasing zeta. Quite right. Now, however, a practical engineer will not try to do that because he doesn't want any zeta. He just doesn't want zeta greater than 0. This is inevitable. You cannot make an inductor without a resistance, because the wire that you are using to wind the inductor has a certain resistance. You don't use an extra resistance unless you want to shape the curve. Suppose you have got such fine, such beautiful wires. Incidentally, the finer the wire, the
higher the resistance.
Higher the resistance. So the lower will be the value of Q. Okay. So you have got thick wires. You have got thick wires, and you have wound them up. Now you find that the resonance is so sharp that it's not useful. If it's very sharp, then the dip will come low. So you intentionally then use a little bit of resistance in the circuit. Resistance in the circuit usually is not added unless your load is resistive. It might appear, it might so happen that the secondary has to transfer power to, let's say, the input of an amplifier stage. The input of an amplifier stage, the impedance is basically resistive. So this resistance is inevitable. Okay, this resistance is inevitable. Then you will have to change your coil and capacitor to be able to adjust to the particular band of frequencies and the sharpness of resonance that you really desire. Okay, now as I had said, yes.
That means you don't have only control over K. You won't change.
We have a control over K. We can bring them closer together or separate out. These are determined by these companies manufacturing IF coils by trial and error, and once they do this, now of course there are computer aided procedures. Once they do this, they keep it fixed, and the manufacturing is also done with computer aids, so that precise control is needed. They cannot afford to manufacture a radio set in which the IF coil is defective. Instead of 465, if the frequency is 490, then the whole set has to be thrown out. And you remember that nowadays everything is manufactured by integrated circuit processing. They are not discrete components. IF coil usually is a discrete component, but it can also be made for very high frequencies by IC inductors, that is by depositing conducting layers in a spiral manner so that it behaves like an inductor. And then there is no way you can correct it. You cannot simply take out the IF coil and throw it. Okay, you cannot replace it, and this replacement is going to be very costly, because if a company has to make profit, they have to make 20,000 in a day, correct? And they cannot go on sampling each of them to find out which one is correct. They cannot take a risk. Yes? Any other question? Look at this now. I have shown two cases. One is critically coupled. The orange curve is critically coupled, and the black one is the overcoupled case. And in both cases, one can find out the half power points omega C1 and omega C2. For this one, by a geometric construction. What about this one, where it is critically coupled? Will the geometric construction work?
Yes.
It will still work. What about the undercoupled case? Let's draw that also. What about the undercoupled case?
So you might not have the half power frequency.
You will have the half power point. You want it or not, you like it or not, it's going to happen. You see, this is the maximum, and then you will have. Is it possible?
Yes.
I leave that answer to you.
It is possible.
Okay. I want you to find out a procedure to do that. We conclude this class with an example. It's a very illustrative example. We have a transfer function of this form: s plus 2 plus j100, s plus 2 minus j100, s plus 2 plus j106, s plus 2 minus j106. This is the transfer function. And one should immediately recognize that it is the transfer function of a double tuned circuit in the manner that we have taken, that is the output across a resistance in the secondary, and the two complex conjugate, the two pairs of complex conjugate poles is minus 2 plus minus j100 and minus 2 plus minus j106, and therefore zeta squared much less than 1, k much less than 1 are automatically satisfied because of the symmetry that the poles obey. Alright. Can you tell me what is omega n in this case? 103. It is the arithmetic mean between 100 and 106. Okay. Now let's find out. I am tempted to continue this example in tomorrow's class. I want to utilize the 3 minutes that are left to tell you something more interesting. In this context, if you get such a transfer function, is it necessarily that of a double tuned circuit? The answer is no, and I want to tell you why. A double tuned circuit, yes, we have shown, we have demonstrated that this is the case. Okay. Suppose we have two tuned circuits. We will continue this example in the Friday class, that is tomorrow. Suppose we have two tuned circuits like this. I have a resistance, inductance and a capacitance VI. I have another tuned circuit like this, and I take the output across this. And for simplicity, let us say they are identically coupled. They are identical tuned circuits. Okay. Now, obviously, if they are like this with else not coupled to each other, that is, this is shielded. You know what is a shielded coil? It's surrounded by a metal which is non-magnetic. Okay. So it shields the magnetic field. Magnetic field is all inside. It cannot couple to anything outside the world. Okay. Most of the coils that you see mounted in let us say radio frequency and lower frequency apparatus, they are all shielded, because otherwise they are going to make havoc. They are going to couple with anything that is nearby and cause havoc. Okay. So they have to be shielded. They are shielded. If there is no coupling between the two, obviously V0 shall be identically equal to 0. But suppose we connect a small capacitor between the two. Suppose we connect a small capacitor between the two. Alright. Will there be a voltage here? I am appealing to your common sense.
So VI is DC or some sinusoidal?
Pardon me?
So VI is sinusoidal?
It doesn't matter. It is a varying. It is a varying voltage. Whatever it is, it could be a sawtooth, for example. Will there be voltage V0 here?
Yes, sir. We are having one terminal connection.
The answer is no.
We may have at least two terminal connections.
You see, what I have done is, I have a circuit here. This circuit 1. Let's have some fun. Then what we have done is, we have a CM, and between this point and this point, this is floating. We have some other. So the essential condition for V0 to appear is that these two should be connected, not necessarily to ground. What is so sacred about ground? It's just a reference. We don't have to go to the temple. I mean, we can have a common point of reference anywhere we like. All right. Okay. There is a similarity between this and what Ramakrishna taught, but we will not go into that. Now, if we have a reference, then only V0 is meaningful. Okay. If Cm is 0, if there is no capacitive, this is called capacitive coupling. Instead of inductive coupling, it is a capacitive coupling. Alright. If there is a Cm, non-zero Cm, then you shall observe exactly the same kind of behavior as in double tuned circuit. Okay. So two tuned circuits can be coupled by capacitance also. This is called electrostatic coupling. Is it possible to replace the capacitor by a resistance? Of course it is possible. Anything connected here, it could be resistance, inductance, capacitance, anything connected here which is non-infinity in impedance. Is that clear? A finite impedance connected here is adequate for coupling two circuits, provided they have a common reference. There must be a common reference. Well, this may be connected straight or may also be connected to another impedance. It doesn't matter. The hybrid coil that you see in telephony is an example of such coupling. Okay, is an example of such coupling. It could be any impedance that you like, provided the impedance is not infinity. If the impedance is infinity, no current can flow, and therefore, okay, this electrostatic coupling can be dealt with exactly the same manner as inductive coupling. The double tuned circuit is an example of coupling through magnetic field. The capacitive coupling is an example of coupling through electric field. If there is a resistance, then if instead of a capacitor or inductive coupling there is a resistive coupling, it is a case of dissipative coupling. That is, whatever energy is there, energy is being transferred, but in the process there will be losses in the coupling resistance. Okay.